Hello from Marchart. I have made a cool mathematical poster for you that you can download from the description below. So what's the poster about? The poster is about a curve called catenary. It's the shape of an ideal hanging chain, supported only at its ends. You can see an imperfect real form of it here. In this video, I will introduce you to those who hear about it for the first time, but I will also show something that may surprise even an expert. Hello?
Oh, hi.
Would you say that this shape is a parabola? I'm in Florence in front of the house of Galileo Galilei, who in 1638 recognized that a catenary is different to a parabola he studied. A hanging chain does not take the shape of a parabola. Trajectories of objects in gravitational field and vacuum do. Let's now take a step back and talk about curves humanity was familiar with first, conic sections. We will see the relevance of them to the catenary soon. If you take a cone and slice it with a plane, depending on how you actually do it, you make one of four classical curves. A circle, if you slice it parallel with the base. An ellipse, if you slice it at an angle but the cut is not yet parallel to the side of the cone. A parabola, if the cut goes parallel with the side of the cone. And a hyperbola, if you make the cut at any steeple angle. That's a cone. On top, there is a circle, and the heel cuts an ellipse. Already at around 200 before current era, Apollonius of Perga has written a systematic work on conic sections. It then took more than 18 centuries for a catenary to be distinguished as a new curve. To see Apollonius' work in perspective of other discoveries, I have made a separate poster on history of mathematics with an accompanying video that you may also watch on this channel. Analytically, we can generate some examples of these curves by taking a common equation with a parameter e called the eccentricity. If e is 0, we get an equation of a circle. If e is between 0 and 1, we get an equation of an ellipse. If e is 1, we get an equation of a parabola. And if e is greater than 1, we get an equation of a hyperbola. Here is an animation that makes a continuous transition between the curves. Please note that this does not give us all such curves. For example, here we get only one parabola while, even disregarding the position of its vertex, there are many parabolic shapes obtained by scaling it with a constant. Geometrically, we can define these curves using a line called the directrix, a point outside this line called the focus, and the already mentioned eccentricity. Let's take a parabola as an example, which has an eccentricity of 1. It is the set of those points A whose distance from the focus is equal to their distance to the directrix. This has profound practical implications. If we take light traveling in parallel rays perpendicular to the directrix and place a parabolic mirror in front of it, all the rays will be reflected so they meet at the focus. After all, that's the meaning of the focus. That's the point where the rays converge. As the rays of light that should converge on your eye's retina after traveling through the lens, but might don't so I wear glasses. Coming back to a parabolic mirror, the light deflected by the mirror travels at the same speed as before, so it travels the same distance as it would have to reach the directrix, and at that distance lies the focus by the geometric definition of parabola. Of course, this alone does not prove that the light reflects under the correct angle to reach the focus, only that it travels the correct distance. I will complete the argument now, but you may safely skip to the next chapter if you are not interested. Let's assume that the ray indeed reflects under the correct angle to reach the focus and work out what the slope of the tangent to the mirror is. Knowing the tangent is knowing the derivative, so integrating the expression will give us the equation of the mirror that does the job. First, the ray coming through the focus must reflect straight back to the focus, so the tangent at the point V has a slope of 0 and V is the vertex. Because of what we said about the distances, the distance between f and v must be the same as the distance between x-axis and the directrix, which is the distance between x and b. Let's now join the focus f with the point B, marking a new point C where it intersects the line Vx. From congruence of triangles FVC and BXC, it then follows that the line Vx cuts FP at half. Since AB and AF are the same, again recall the geometric definition of parabola, CA must be the tangent and acts at the point A as our mirror. Now we need to work out its slope. If you remember that the angles in a triangle always sum up to 180 degrees, or p radians, you will have no trouble working out that the angle FBE is also alpha. Show me your work in the comments. That makes triangles FEB and CXA congruent, and the slope of the line CA, which is the ratio of XA to CX, is the same as the ratio of EB to FE. So that the equation comes out nicely, let's pick the distance FE to be 1 over 2a and EB to be x. The ratio of XA to CX, which is also the slope of the line CA, is then 2ax. This holds for any x, as the case of x being 0 was the case of the vertex v. Integrating this expression, we indeed get the equation of parabola ax squared plus a shift in the y-axis. Let me repeat the idea of the proof again. We first started with the geometric definition of parabola. We then pretended that we did not know its slope at the general point, but figured it out by requiring the parallel rays to reflect into the focus. Finally, we integrated the general slope formula to get the familiar equation of a parabola. This property of parabola, focusing parallel rays into a single point, made its use in antennas and telescopes. Actually, professional astronomers prefer to use hyperbolic mirrors for certain corrections, but cheaper telescopes use parabolic mirrors as those are easier to make. A parabola even forms at the surface of a rotating liquid, a principle that is used in liquid mirror telescopes. Now we are going to work out the connection between conic sections and a catenary. Let's start with goniometric functions. Sine, cosine, tangent. What are they about? Gonio means angle, metry means process of measuring. So they are about angles. Angles are best associated with arcs of a unit circle. So the angle alpha, in radians, is actually the length of the green arc. From there, the functions are defined in truly simple way, as the lengths of the shown line segments. Everyone should remember this definition, and it makes memorizing many properties and identities easy. For example, we get directly from the Pythagorean theorem that the square of sine plus the square of cosine of the same angle gives 1. Now, hyperbolic functions, you guess it, are defined using a hyperbola. More precisely the unit hyperbola, which is eccentricity of the square root of 2 and its asymptotes are perpendicular. While in the case of cosine we use an arc length as its argument, the argument of hyperbolic cosine is the green area S. Finally, the graph of hyperbolic cosine, when you put its argument on the x-axis, well, that's a catenary. Here we have a hyperbolic cosine graph. You can have this poster. Just keep watching. It's a perfect match. We should make a note about suspension bridges. Their cables are not free hanging, they support the weight of the rod underneath. In reality, the shape of the cable is somewhere between that of a catenary and a parabola, but much closer to a parabola due to their weight being much smaller than that of the rod. Maybe you knew what catenary was, but did you know that the ratio of its length, which you can get by integrating the square root of 1 plus the derivative squared, to the area between the curve and the x-axis, which you can get by integrating the function of an interval, is constant? Let's repeat that again. The ratio of the catenary's length and the area between it and the x-axis is constant, regardless of which interval of the particular catenary curve we look at. Wow! In fact, as Edward Parker has shown in his paper that is referenced in the description of this video, among twice differentiable functions, the only other function with this property is a constant function. The proof of this is rather straightforward. We can first ignore the integrals and get this nice equation that I have denoted here with a star. A constant function obviously satisfies it. Its derivative is 0, so this starred equation just gives us back a constant function. If the function is not a constant, then we can separate variables and find the solution of this differential equation by simple integration. Alright, even if you knew differential equations, the mathematics is not so simple that you can immediately see the result. If you are interested, just download the poster and spend few moments thinking about the proof. However, everyone who made it this far can understand that the catenary satisfies the property, that hyperbolic cosine satisfies the starred equation as a constant function then. As we already know how hyperbolic cosine is defined, and we know also how hyperbolic sine is defined, we get the identity squared hyperbolic cosine minus squared hyperbolic sine over the same area S equals 1. This is very similar to the Pythagorean identity for cosine and sine functions, except the minus sign. You see how useful geometric definitions are? Now, because hyperbolic cosine gives positive values, our catenary is about the x-axis, we can express hyperbolic cosine as a square root of 1 plus the square of hyperbolic sine, and multiply both sides of the resulting equation by our parameter a. From here we get the starred equation if we realize that the derivative of hyperbolic cosine is simply hyperbolic sine, and apply the chain rule, which eliminates the constant a in front of the derivative. Wait, why is the derivative of hyperbolic cosine hyperbolic sine? The simplest proof would involve rewriting hyperbolic functions using exponential functions, but I feel that this video is already long enough, so I will leave it like that, which concludes the proof of the fact that the area between a catenary and the x-axis divided by the catenary's length is constant regardless of the interval considered. And here you have it, from conic sections to catenary in one math chart. You may download it from the description below, and I will also select one or more individuals among commentators on my channel to whom I will physically post the poster by mail for free. Best wishes from Math Chart!